Preparing for a drone test engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you create a test plan for a new multirotor drone before its first flight? I would avoid jumping directly to free flight. First, I map requirements to test cases, then run bench checks for power, firmware, sensors, ESCs, motor direction, fail-safes, and telemetry. After calibration, I perform restrained thrust tests and a low-altitude hover in a controlled area. Every phase has pass criteria, logs, and abort conditions. The goal is to discover integration issues safely before expanding the envelope. While answering, focus on phase testing, requirements review, bench checks, sensor calibration, motor direction, tethered tests, controlled hover, risk assessment, success criteria, logging, and rollback procedures. Question 2. What key parameters do you verify during pre-flight checks for a drone? A good pre-flight check is about removing known risks before arming. I verify propellers, frame, landing gear, payload mount, battery voltage, cell balance, GPS fix, compass health, IMU calibration, RC link, telemetry, and firmware configuration. I also check wind, rain, airspace, home point, geofence, and return to home altitude. If any critical item is uncertain, I do not fly. Discipline here prevents most avoidable incidents. Make sure to cover hardware integrity, battery health, GPS lock, compass and IMU status, propeller condition, firmware version, geofence, fail-safe settings, payload attachment, environmental conditions, and communication link quality. Question 3. How do you test and validate a drone's fail-safe behavior? Fail-safe testing must be controlled and staged. I first validate behavior in simulation or HIL, then in a safe field with altitude limits and recovery plans. I test RC loss, telemetry loss, low battery, GPS degradation, geofence violation, and return to home triggers. I verify whether the drone lands, loiters, returns, or disarms as configured. The pass condition is not just activation, but predictable behavior with correct timing and logs. In your answer, talk about simulating link loss, low battery, GPS loss, geofence breach, motor failure where applicable, return to home behavior, altitude settings, safety boundaries, and log-based validation. Question 4. What is the difference between SITL and HIL testing in drone development? SITL runs the flight stack in a simulated environment without real hardware, so it is fast, cheap, and repeatable for mission logic, navigation, and regression tests. HIL adds real flight controller hardware connected to simulated sensors and actuators, so timing, interfaces, and hardware behavior are tested more realistically. I use SITL early and often, then HIL before flight. Neither replaces field testing, but both reduce risk dramatically. Be sure to mention software in the loop versus hardware in the loop. When each is used, fidelity differences, sensor and actuator simulation, cost, repeatability, and limitations before real flight testing. Question 5. How would you diagnose a drone that drifts during hover, even in calm wind? I would start by separating sensor, mechanical, and control causes. I check IMU and compass calibration, GPS quality, EKF status, vibration levels, motor balance, propeller condition, and center of gravity. Then I review logs for position error, attitude correction, and accelerometer bias. If sensors are clean but drift remains, I look at PID tuning and airframe symmetry. Hover drift is rarely one magic setting. It is usually evidence-driven debugging. While answering, focus on root cause isolation across IMU calibration, compass interference, GPS accuracy, accelerometer bias, vibration, center of gravity, prop imbalance, PID tuning, and log analysis. Question 6. What logs or telemetry data are most useful after a failed drone test flight? After a failed flight, I want enough data to rebuild the timeline. The key logs are mode changes, arming state, RC commands, attitude set points versus actuals, motor outputs, GPS fix, EKF health, IMU vibration, battery voltage sag, current draw, and fail-safe events. I correlate these with video and pilot notes. Good analysis avoids guessing. I identify what happened first, then what was merely a consequence. Make sure to cover flight mode changes, battery voltage, current, GPS status, EKF innovations, IMU vibration, RC input, motor outputs, attitude errors, fail-safe triggers, timestamps, and event reconstruction. Question 7. How do you validate IMU, compass, barometer, and GPS sensors on a drone?
Sensor validation starts with clean calibration, then consistency checks. For the IMU, I verify bias, noise, temperature behavior, and vibration response. For compass, I check heading accuracy and magnetic interference from power wiring or payloads. For barometer, I compare altitude stability indoors and during climbs. For GPS, I assess satellite count, HDOP, lock time, and position repeatability. I trust sensors only when static tests and flight logs agree. In your answer, talk about calibration procedures, bias checks, sensor consistency, environmental interference, vibration isolation, static and dynamic tests, cross-sensor comparison, and acceptance thresholds. Question 8. How would you test battery performance and power reliability for a drone? Power testing is both performance and safety work. I inspect battery health, cell balance, internal resistance, connector condition, and charger records. During bench and flight tests, I monitor current draw, voltage sag, temperature, and discharge curve under different payloads and maneuvers. I validate low battery warnings and return to home margins with reserve capacity. A drone may fly perfectly at full charge, but fail when voltage sags under aggressive throttle. Be sure to mention cell balance, internal resistance, voltage sag, discharge curves, current draw, thermal behavior, connector integrity, flight endurance, payload impact, low battery thresholds, and safety handling. Question 9. What steps would you take if a motor or ESC overheats during testing? First, I stop the test safely and avoid repeated thermal stress. Then I compare the hot motor or ESC against the others: current draw, RPM, propeller condition, bearing smoothness, alignment, solder joints, and cooling airflow. I check whether the prop size or payload is overloading the system, and whether ESC firmware protocol settings are correct. If one arm runs hotter consistently, I swap components to isolate motor, ESC, wiring, or frame issues. While answering, cover safe shutdown, inspecting propeller load, motor alignment, ESC rating, current draw, cooling, solder joints, firmware settings, PWM shot configuration, bearings, and comparative testing across arms. Question 10. How do you approach PID tuning for a drone flight controller? PID tuning is about making the drone responsive without oscillation. I start from a stable baseline, tune rate loops before position behavior, and make small changes one axis at a time. Too much P creates sharp oscillation, too much I can cause slow windup, and too much D can amplify noise or heat motors. I use logs, step responses, and controlled maneuvers. Payload and prop changes require retuning, not assumptions. Make sure to cover rate versus angle loops, oscillation symptoms, step response, overshoot, damping, payload differences, log-based tuning, incremental changes, safety limits, and test environment control. Question 11. How would you verify autonomous waypoint mission execution? I validate waypoint missions in layers. First, I review coordinates, altitude frame, speed, yaw commands, geofence, and return behavior. Then I run the mission in simulation, followed by a small field test with conservative altitude and a pilot ready to take over. After flight, I compare planned versus actual path, waypoint acceptance radius, timing, and deviations. A mission passes when it is safe, repeatable, and within defined navigation tolerances. In your answer, talk about mission upload validation, GPS accuracy, geofence, altitude references, speed limits, yaw behavior, obstacle constraints, loss of link behavior, acceptance criteria, and post-flight path comparison. Question 12. What communication links do drones commonly use, and how would you test link reliability? Drone links usually include RC control, telemetry radios, video links, Wi-Fi, LTE,
or custom RF. I test reliability by measuring RSSI, packet loss, latency, range, antenna orientation effects, and interference in realistic environments. I also validate what happens when the link degrades, not just when it works. The important question is whether control, telemetry, and fail-safe behavior remain predictable before the aircraft reaches unsafe conditions.
Be sure to mention RC control, telemetry, Wi-Fi, LTE, radio modems, latency, packet loss, range testing, interference, antenna orientation, fail-safe triggers, encryption, and regulatory frequency constraints.
Question 13. How do you test obstacle avoidance or collision avoidance features on a drone?
Obstacle avoidance testing must be staged because failures are physical. I begin with sensor bench tests for range, field of view, latency, and detection of different materials. Then I use controlled low-speed scenarios with foam obstacles, nets, or tethers. I vary lighting, angles, textures, and approach speeds. I also test false positives and override behavior. A good system should avoid obstacles without becoming unpredictable or overly conservative. While answering, focus on sensor type, detection range, false positives, false negatives, lighting, surface material, approach speed, test rigs, safety nets, scenario coverage, and manual override.
Question 14. How would you perform environmental testing for a drone? Environmental testing defines where the drone can safely operate. I test temperature effects on batteries, sensors, motors, and plastics. Wind tolerance during hover and navigation, dust or moisture exposure based on IP rating, and vibration over repeated flights. I also observe GPS and barometer behavior at different conditions. The output is not just pass or fail, but a documented operating envelope with limits, warnings, and maintenance implications. Make sure to cover wind, temperature, humidity, dust, rain exposure if rated, vibration, altitude, thermal limits, material behavior, sensor effects, ingress protection, and documenting operational envelopes. Question 15. What regulatory and safety considerations matter during drone test flights? A drone test is an aviation activity, not only an engineering activity. I check local regulations, airspace restrictions, altitude limits, pilot certification needs, visual line of sight rules, remote ID requirements, and permissions for the test site. I also define roles, emergency procedures, exclusion zones, and abort criteria. Safety planning protects people and the company. Even a technically successful test is unacceptable if it violates airspace rules. In your answer, talk about local aviation rules, airspace permissions, visual line of sight, remote ID where applicable, test area control, emergency procedures, risk assessment, insurance, and incident reporting. Question 16. How do you handle regression testing after a flight controller firmware update? I treat firmware updates as high-risk changes until proven otherwise. I review release notes, backup parameters, run SITL or HIL regression cases, and verify calibration, arming, flight modes, telemetry, fail-safes, and mission behavior. Then I perform limited real flights against a known baseline. I compare logs for attitude stability, sensor health, and mode transitions. A rollback plan is mandatory because a small firmware change can affect safety-critical behavior. Be sure to mention release notes, version control, test matrix, simulation, HIL, parameter migration, sensor calibration, core flight modes, fail-safes, logs, rollback plan, and comparison against baseline behavior. Question 17. How would you investigate a sudden loss of altitude during flight? I would reconstruct the event from logs instead of assuming pilot error. I check battery voltage sag, current spikes, motor outputs, throttle saturation, attitude changes, vertical velocity, barometer readings, GPS altitude, flight mode, and RC input. Then I inspect props, motors, payload attachment, and frame damage. Sudden altitude loss often comes from insufficient thrust margin, power issues, sensor error, or aggressive maneuvering. The timeline tells which one happened first. While answering, cover timeline reconstruction, battery sag, thrust margin, prop or motor issues, barometer error, GPS altitude, pilot input, payload shift, wind, flight mode, and controller saturation. Question 18. What is geofencing and how would you test it on a drone? Geofencing creates virtual limits that prevent the drone from leaving an approved area or altitude. I tested first in simulation, using boundary crossings, GPS noise, mission paths near edges, and different breach actions. In the field, I use conservative distances and verify warnings, mode changes, return to home, or landing behavior. I also test startup outside the fence and poor GPS conditions. Geofence logic must fail safe, not surprise the pilot. Make sure to cover virtual boundaries, altitude and radius limits, polygon zones, GPS dependency, warning behavior, breach response, return to home or landing actions, simulation, field validation, and edge cases. Question 19. How do you evaluate payload impact on drone performance? Payload changes the aircraft, so I compare against a no-payload baseline. I measure added weight, center of gravity, mounting stiffness, vibration, power draw, hover throttle, flight time, and thermal behavior. Then I test stability, braking, waypoint accuracy, and emergency maneuvers. A payload that is mechanically secure can still reduce thrust margin or disturb sensors. I approve it only when performance remains inside safety and mission requirements. In your answer, talk about weight, center of gravity, vibration, mounting rigidity, power consumption, endurance, thrust margin, flight stability, calibration changes, mission accuracy, and repeated tests with baseline comparison. Question 20. Describe a structured root cause analysis process for a drone crash or near miss. After a crash or near miss, I preserve evidence before changing anything. I collect flight logs, video, telemetry, firmware versions, parameters, battery data, weather, and pilot statements. Then I build a timeline and identify the first abnormal event, separating root cause from damage effects. If reproduction is needed, I use simulation or controlled bench tests first. The final output is corrective action, verification testing, and documented prevention. Be sure to mention preserving evidence, collecting logs, interviewing operators, building a timeline, separating primary and secondary failures, reproducing safely, corrective actions, verification tests, and documentation. If you are still with us, congratulations. You are much ahead of the rest. I'm serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.